All right, so here's a second worked example with Le Chatelier's principle. We're going to be basing most of our reasoning on using the reaction quotient to decide the direction the reaction shifts as we apply different stresses. Remember that Le Chatelier's principle tells us that if you start with a reaction at equilibrium, we have a reaction here and we're going to assume it's at equilibrium in a rigid closed vessel, and then you apply some stress which causes one of the rates, forward or reverse, to change, then as a result, the equilibrium shifts. The reaction shifts forwards or backwards in order to relieve that stress and achieve a new equilibrium. So that's Le Chatelier's principle. Now, looking at this reaction, we notice that it's heterogeneous, like the first example we saw. The water in the product there is a liquid, okay, so keep that in mind. And we're told here delta H, the heat of reaction, is negative 122 kilojoules per mole. The number itself doesn't really matter to me, but the sign that's negative tells me that this reaction, as it's written above, is exothermic. Okay, and negative delta H means that the forward reaction here is exothermic. So the reverse reaction would be endothermic and would have a positive delta H. Now, if we know that the forward reaction is exothermic, then one thing that immediately comes to mind is the relationship between Kc and temperature. Okay, as soon as you know that it's exothermic, you should sketch this little graph. So this tells me that when temperature increases for this reaction, Kc will decrease. Or if temperature decreases, Kc is going to increase. Okay, that's the relationship of Kc to temperature for exothermic reactions. Now the question's asking us to predict what will happen to the amount of chlorine in the vessel. So we look at chlorine, it's on the right-hand side of our equation. Okay, so chlorine is a product. So that means if this reaction were to shift forwards, we would produce more chlorine. So if we have a forward shift, the amount of chlorine will increase. If it shifts backwards, then the chlorine is going to get used up. So shifting backwards, we'd have less chlorine at the new equilibrium. All right, so a forward shift makes more chlorine, and a backward shift uses up chlorine, so we'll have less. So to predict the direction of the shift, we're going to look at the reaction quotient. You can pause the video here and write for yourself the reaction quotient for that reaction. Q is going to equal the concentration of chlorine squared divided by the concentration of HCl to the fourth times the concentration of oxygen. Remember to leave out the water because it was liquid. It's not going to be part of the expression for Q. Also remember that when Q is less than Kc, it results in a forward shift. If Q is greater than Kc, it gives us a reverse shift in equilibrium. If Q is equal to Kc, which is what we have at the beginning before we do any stresses, then the system is at equilibrium and there's no shift, right? There's no shift forwards or backwards if you're at equilibrium. So Q equals Kc, there's no shift. All right, so with that in mind, you should pause the video as needed. So let's look at the first stress. We're going to cool the system down. Okay, that's the first thing. So jot that down in your notes. Cool the system down. What will happen to the amount of chlorine if we do this? Well, first we look at Q and we recognize that cooling the system doesn't change any of the concentrations in Q. So cooling the system has no effect on Q, so Q is unchanged. That would be the first thing I would put in my answer. Q does not change. But looking at the graph that we sketched, we can see that when you cool the system down, you lower the temperature, the Kc gets bigger, right? So that would be the next thing I would say. Because this reaction is exothermic, cooling causes Kc to increase. Okay, pause the video if you need to jot these things down. So we said Q didn't change, we said Kc increased. So the next thing I would say is, therefore Q is less than Kc. If Q didn't change but Kc got bigger, then Q is now less than Kc. And as we just mentioned, when Q is less than Kc, you get a forward shift in equilibrium. And if you shift forward, you're going to produce more chlorine. So the amount of chlorine would increase. All right, so check the answer you wrote down. Did you say the following things? Number one, Q is unaffected. Q doesn't change. Number two, that Kc increased when you cooled a system because this was an exothermic reaction. Did you then say that Q is now less than Kc? Did you say that that would cause a forward shift in equilibrium? And finally, did you say that that'll produce more chlorine at the end? That would be a complete answer. All right, so let's look at another one. Okay, so the second stress tells us that we've added more oxygen. So jot that down. We're adding more oxygen. What will happen to the amount of chlorine as a result of that? Well, first thing is to look at Q. Oxygen is in the denominator of Q. So the first thing in my answer would be that I've increased the concentration of oxygen. Then I would say this will cause Q to decrease because oxygen's in the denominator. If you have a larger concentration of oxygen, you're dividing by a larger number, Q will get smaller, right? So Q will decrease. The next thing I would say is that Kc is unaffected because the only thing that changes the Kc is changing temperature. So adding oxygen doesn't affect Kc. So Q got smaller and Kc didn't change. If you think about that, then that means that Q is now less than Kc. That would be the next thing I'd put. Q is less than Kc. And now it's the same as the last example. If Q is less than Kc, that will cause a forward shift in equilibrium, and you'll end up producing more chlorine gas. So check your answer. Did you put the following statements? Did you say that more oxygen added will cause the oxygen's concentration to increase? Did you point out that Q will decrease because oxygen's in the denominator? Did you mention that Kc doesn't change because the temperature didn't change? Did you say that Q is now less than Kc? It'll cause a forward shift in equilibrium and therefore produce more chlorine. All right, the next stress tells us that water is added. Okay, so we're going to add more water to the system. If you think you know what you're doing, pause the video and try to answer that yourself. All right, so I hope you don't get tricked. Water is not in the expression for Q because it's a liquid, therefore it's left out of Q, right? So water will have no effect on the value of Q. Adding more water has no effect on Kc because it's not changing the temperature, Kc doesn't change. So because Q didn't change and Kc didn't change, Q is still equal to Kc. Q is equal to Kc, and therefore no shift occurs, and nothing will happen to the amount of chlorine. No shift because Q is still equal to K, and chlorine stays the same. All right, the next stress says we're going to remove some HCl. Pause the video and see if you can answer that yourself. So removing HCl, the first thing you should say is that it causes the HCl's concentration to decrease. Looking at Q, HCl is in the denominator. So if the HCl's concentration decreases, you're dividing by a smaller number, that will cause Q to get bigger. Q will increase because you're dividing by a smaller concentration. Kc is unaffected because temperature didn't change. Therefore, Q is now bigger than Kc. So a backward shift in equilibrium will occur. And if the reaction shifts backwards, it will use up some of the chlorine. You'll end up with less chlorine at the new equilibrium. Okay, so check your answer one more time. You removed HCl, causing HCl's concentration to drop. With a smaller HCl concentration, Q gets bigger. You're dividing by a smaller number. Kc didn't change because temperature didn't change. So if Q got bigger and K didn't change, Q is now bigger than Kc. And that causes a reverse shift in equilibrium. And if the reaction shifts reverse, you'll have less chlorine because chlorine is on the right side of that equation. All right, try the next one. This time we're going to add a catalyst to the system. What does that do to the amount of chlorine in the container? Well, the catalyst doesn't affect the concentrations of any of the things that are in Q. It doesn't change any of those concentrations, so Q is unchanged. And the catalyst doesn't affect Kc because only temperature affects Kc, so Kc is unchanged. So if Q is unchanged and Kc is also unchanged, Q and Kc are still equal and no shift will occur, so nothing happens to chlorine. That would be a complete answer. Now the catalyst does cause the forward and reverse reactions to speed up. The catalyst lowers an activation energy. If you recall from our kinetics lessons, the forward and reverse reactions speed up, but they speed up equally. So when they started off at equilibrium, the two rates were equal. When after adding a catalyst, the forward and reverse rate are both faster, but they're still equal. So there's no shift in equilibrium. And then the last one is the hardest one of these. We're going to change the volume of the container. We're going to increase the volume of the container. Pause the video and see if you can explain what will happen. Increasing the volume of the container, if you remember our formula, C equals N over V, with a larger volume, all of the concentrations will drop. Okay? All concentrations of gases in that container will drop. So the chlorine concentration drops, the oxygen drops, the HCl drops. Now looking at the expression for Q, Q is going to be affected here because the numerator, if you look at the exponent for chlorine, it's a 2, so the numerator is second order. The denominator, oxygen's exponent is a 1 and HCl is a 4, so 4 plus 1, that's fifth order. Now, if the orders on the top and bottom had been the same, if they were the same order on top and bottom, then the numerator and denominator of Q would be affected equally. And if they're affected equally, then Q doesn't change. If the top gets smaller and the bottom gets smaller by the same amount, then the ratio is the same. But in this case, the denominator has a higher order. The denominator is fifth order. So while the top and bottom both get smaller, all the concentrations are dropping, the denominator will get even smaller because it's a higher order. So if the denominator gets even smaller, then you're dividing by something even smaller. That will cause Q to increase. So increasing the volume caused all the concentrations to drop. Since the denominator of Q has a higher order than the numerator, then the denominator will get smaller than the numerator. And if it gets even smaller than the numerator, Q will get bigger. You're dividing by a smaller number, the answer will be bigger. So Q increases. The temperature didn't change, so Kc stays the same. Therefore, Q is now bigger than Kc. And if Q is bigger than Kc, the equilibrium shifts backwards. Shifting backwards, the chlorine's concentration will go down. All right, so that one, you had to consider the orders on top and bottom in Q to figure out what happened. It's a little bit tougher. Okay, so this next one, I'm going to get you to treat this more like a multiple choice question. So I'm not going to fully explain everything. If you're not sure of one of my answers at the end, you can ask me in class or ask me on Classroom. So we have a new equilibrium. We notice again that it's heterogeneous. There's solid on the left. There's also solid on the right. All right, so you should pause the video, write the reaction down, and then write the expression for Q. So Q here is going to equal the concentration of the H2O to the fourth over the concentration of H2 to the fourth. We leave out the solids on the top and bottom. We're told that the reaction is endothermic, right? So delta H for the forward reaction is positive. If the word heat were included, heat would be on the left side of the equation because it's endothermic. Now, why do I care about the endothermic? Because if it's endothermic, then the relationship from Kc to temperature is this, right? So Kc will increase when temperatures increase. Kc will decrease when temperatures decrease for an endothermic reaction. Okay, so now we're asking here, what happens to the amount of iron? The iron is the product on the right-hand side if we do these various stresses. Now, some people might think because the iron is a solid that it doesn't change. Well, notice the question doesn't ask what would happen to the concentration of iron, because if it said that, well, the answer would be nothing changes because solids have constant concentrations. That's why we left them out of the expression for Q. But it doesn't say concentration, it says amount of iron. The amount is like the mass or the moles. If this reaction shifts forwards, it's going to produce more iron, so the amount of iron would increase. If it shifts backwards, it has to use up iron, so the amount of iron would decrease. So even though it's a solid, the reaction shifting forwards or backwards would affect the amount of that solid. Okay? Same thing for liquids. If the reaction shifts, liquids and solids and gases and aqueous things will change in amount. But liquids and solids, they don't cause changes to occur. But when a change is happening, everything will increase or decrease. All right, so pause the video, see if you can explain what happens in these different stresses. You can either fully explain if you like, or you can think about it in your head and just put an answer down beside it. Will the amount of iron increase, decrease, or maybe stay the same if you do these different things? Okay, so pause the video and see if you can figure these out. So the first one, the volume doubled, so the volume increased. And you remember C equals N over V, so if the volume increases, the concentrations of everything, all the gases, will decrease. So the water vapor and the hydrogen gases will both decrease. So when that happens, we look at Q and we notice that the numerator decreases and the denominator decreases. So when that happens, we have to look at the orders on top and bottom. In this case, the order on top is a 4, the order on the bottom is also a 4. That means they're equal, and if they're equal, Q will not change, right? So decreased on top and decreased on the bottom by the same amount means Q will stay the same. If Q stays the same, Kc also stayed the same because temperature didn't stay the same, didn't change, so therefore nothing happens. There's no shift, so there's no change to the Fe. Hydrogen gas is removed from the flask, so its concentration drops. Hydrogen's in the denominator of Q, right? It's on the bottom of the expression for Q. So if you have a smaller denominator, Q gets bigger. Kc didn't change because temperature didn't change. Q is bigger than K. That's going to cause a reverse shift. The amount of iron will decrease. If you add iron oxide to this flask, well, the iron oxide is a solid. Adding more of the solid doesn't affect Q because it's not in the expression for Q. It doesn't affect Kc because only temperature affects Kc. So Q and Kc are unchanged and they're still equal. There's no shift. If there's no shift, there's no change to the amount of iron. If you heat the flask, Q will be unaffected because the concentrations are unaffected by that. The volume of the container was rigid. It doesn't change when you heat it, so the concentrations don't change. So Q doesn't change. Looking at our graph, though, if you heat the flask, the temperature goes up. That will cause Kc to go up because this was endothermic. So if Q didn't change and Kc got bigger, Q is now less than Kc, and a forward reaction will occur. If the reaction shifts forwards, we're going to produce more iron, so it'll increase. Adding helium gas to the flask, well, helium is not in the expression for Q, so it doesn't affect Q, right? The volume of the container is constant, so Q doesn't change. Helium won't affect Kc either because only temperature affects Kc. So Kc and Q are unchanged. They're still equal to each other. That means we'll have Q equal to Kc still, which means there's no change. There's no shift. And the last example, if we add water vapor to the flask. Well, water is in the expression for Q. It's on the top. It's in the numerator. So if you add water, you're going to increase water's concentration. Since it's on the top, that causes Q to increase. Kc is unaffected because temperature didn't change. So Q is now bigger than Kc, and that causes a reverse shift. A reverse shift means the iron will decrease. All right, so I hope you were able to explain that in your head or maybe on a piece of scrap paper, and that's how you would answer for a multiple choice style question. All right, so I realize this may be confusing. If you have questions, we're going to discuss Le Chatelier again in class before our test, so you'll be able to ask questions then.